Our last segment here at Academy for Allied Health, Biomedical Sciences, Mr. Smith, our last area of thermodynamics. We're going to be taking a look at the second law of thermodynamics. We've been going through all these thermodynamic heat systems. The point has been to understand physically what's been going on and again what they're utilized for. So we want to recognize why the second law of thermodynamics requires two bodies at different temperatures for work to be done. And we're going to calculate the efficiency of a heat engine. And then we're going to relate the disorder of a system to its ability to do work or to transfer energy as heat. So we've talked about entropy. We talked about Gibbs free energy. We talked about spontaneity in the area of chemical reactions. In this physics, we're going to deal with thermodynamics strictly from a second law and from a physical standpoint. So the second law of thermodynamics says heat only flows one way, and that is from high energy to low. It also holds that heat cannot be entirely converted into work. In other words, the heat engines, by definition, will send heat to the surroundings in a fashion other than work. That's one of the things that we had to get used to with the first law of thermodynamics and the equation about internal energy. When we change internal energy, are we measuring heat? Yes, we certainly are. But it's heat inside that system. This is where we have to be real careful of defining and understanding our frames of reference. When we have or are able to get an isothermal system and we can make sure that no energy is transferred, no internal energy is transferred from our system as heat, then all of the internal energy can be used for work. Okay, that's the first law. The first law says, by its equation, it says it's possible. There's a possibility Q can equal 0. The second law, however, hangs that up. The second law says, well, yeah, heat will flow, but it only flows from high energy to low energy. So then that means you can't entirely convert it all into work, because it might head towards doing the work, but once it's reached some kind of equilibrium, I mean, there's still heat, but it's no longer going to get converted into work. Okay, so what you have is net work equals net heat, which equals the difference from the high to the low, which means work can never equal QH in a cyclic process. So it can never equal the entire heat of that heat engine. We will lose some energy to the surroundings. It's going to get lost. That's the nature of the beast. That's where the Carnots don't work. So when we talk about heat energy engine efficiency, that's the measure of how well an engine operates. Useful energy taken out relative to the total energy. That's efficiency. So efficiency is net work over the energy or the heat of the system. Okay, so we have it as QH minus QC over QH, or you could have it as 1 minus QC over QH. All of these are valid. Efficiency is a unitless number. It's really more like a percentage. Okay, you're going to get a decimal. So let's try a problem. We're going to find the efficiency of a gasoline engine that during one cycle receives 204 joules of energy from combustion and loses 153 joules as heat to exhaust. Okay, so what do we want to define? What are our givens? QH is 204. Our QC is 153. Our unknown is the efficiency. This is in a diagram of our engine. Okay, it's going to use 204 joules of heat, 153 pop out. Okay, always plan. That's our next step. Choose an equation or situation. Efficiency is ratio of work done by the engine of the heat of the energy, or engine to efficiency is ratio of work done by the engine to the energy transferred to it as heat. All right. Net work, which of course is QH minus QC, or 1 minus QC over QH. calculate it out, substitute the values. This is almost like doing percent error. Okay, so or efficiency or yeah, percent yield actually, right? Percent yield from stoichiometry. So we have the 1 minus 153 over 204. You get 0.25. So the efficiency is about 25%. Okay, only 25% of the energy added as heat is used to do the work. Efficiency is certainly less than 1 as expected. Now, heat engines are inherently inefficient, which, again, for me, gives me something to ponder. It's something that I'm not understanding yet. My guess is it's being left for your generation, because my generation certainly didn't figure it out. And that is, what can we use other than the heat engine cyclic process model to generate power that we need? Because that's what we use with this cyclic process. The other part of the second law determines that a system will go from order to disorder. It talks about entropy. So this flow of energy happens all the time. And because of this energy coming in, it creates greater disorder. So the greater the entropy, the greater the disorder. We know this. Entropy is letter S, right? So the entropy of a system tends to increase no matter what. Of course, greater disorder means there's less energy to do work. So a heat engine over time, what happens with engines? What happens with your car engine? Every now you got to go in for service. Why? Because it gets this greater disorder. It gets broken down. Parts start to come apart. Things start to break down, you have to replace them. So, for example, if all the gas particles in a chamber move toward that piston, the internal energy can use for work, all of it. That would be a well-ordered system, but it's not possible. Okay, so that view on the left isn't possible. You need the view on the right. That's really what happens. Average efficiency, highly probable distribution of velocities. That's just where that goes. So the entropy of the universe increases in all natural products. The universe is increasing its entropy. Hubble was the one who made that statement. Einstein did not like this statement. It's probably the only thing about him that we can say is truly flawed. And that is, he did not like this idea that there is no underlying order to the universe. He always believed that you could have this underlying order. The fact of the matter is that our very existence demonstrates there is great disorder in the universe. And that disorder continues. And Hubble has said that the galaxies and the planets keep moving farther and farther away from each other, which means there's ever more disorder. So entropy can decrease for parts of systems. So you can decrease entropy. However, what they say, there's the old saying, a butterfly flaps its wings in China, and there's a hurricane in Boston. The idea being that a decrease in entropy in one spot must be offset by an increase somewhere elsewhere in the universe. So, in looking at the entropy changes of a refrigerator, because the refrigerator is less than perfect efficiency, the entropy of the outside air molecules increase more than the entropy of the freezing, then the entropy of the freezing water decreases. Okay? Before freezing, you have water. After freezing, the ice looks very ordered. But in the exhaust, before water freezes, look how it looks. And then after it's frozen, look, greater increase. That's because of all that extra heat coming out of the back. Feel the back of your refrigerator sometime. Actually, you can feel certain areas, and it's really, really hot. That's where the heat is getting exhausted. Okay, that's why we have in that one group work we were working on, we talk about opening the refrigerator to cool the room. How it's not going to happen? This is why. Because in the back, you've got that heat coming out. All right, that is thermodynamics. That is heat. Thanks very much. Now we can get in, get some work done, and get ready for a test on 2 chapters. See you in class.